Today we're continuing to look at pH curves, and we're going to take a look specifically at monoprotic versus polyprotic reactions as well as buffers. So a polyprotic acid is going to react more than once with a strong base. You'll note that we never combine a weak acid and a weak base together. And the reason that we don't do that is it becomes very difficult when you have two equilibriums going on simultaneously to get useful data. So we always will end up using a strong monoprotic acid or a strong monoprotic base as our titrant. And it's actually really easy for the bases. All of the strong bases are monoprotic. The polyprotic ones generally don't have good solubility in water. And all of the strong acids except sulfuric acid are monoprotic. So we often don't use sulfuric acid as a titrant unless we specifically need sulfuric acid for the reaction that's taking place. Now, monoprotic acids and bases, they can give or accept more than one proton. And what that means is that the pH curve changes so that we actually see two equivalence points instead of just one. And we get additional buffering zones, the relatively flat regions, for every equivalence point that we add as well. So just by looking at this diagram, I can tell that we are dealing with two acid-base reactions. Now, important thing is, as I mentioned in the last video, sometimes you see slight curves at the very beginning. There is no equivalence point here. Sometimes you will see this in weak acids and weak bases, but what it is actually the reaction, the creation of a buffer region within that acid. If we're talking specifically about something that is diprotic, that means two protons can be transferred. Polyprotic is often used to encompass two or more though, because poly just means many. However, even if a substance is polyprotic, not all of the proton transfers may completely take place. So they may or may not show up on a pH curve. Even in this diagram that we have here, we see it's for H3PO4. There should actually be one more curve up here. We just have not added enough sodium hydroxide to trigger that final release. And when this happens, we get this stepwise reaction because of the decreasing strength each time a polyprotic acid or base reacts. You'll always have the strongest chemical reacting. Just like with redox reactions, we always have the strongest oxidizing or reducing agent reacting. While acid-base reactions, we always have the strongest acid and the strongest base reacting. So that means that polyprotic acids and bases lose one proton at a time. You're not going to have any H2PO4 reacting if you still have H3PO4 present, because the H3PO4 is a stronger acid than the H2PO4 minus. Now we also have these buffer regions that we want to talk about a bit. A buffer is specifically a combination of any weak acid or base with its conjugate base in the same solution. Really important thing about that is it has to be a weak acid. The three things that you never see in a buffer are hydronium, hydroxide, and water, because those are your strong acids and bases, and water is the conjugate for both of them. They cannot buffer because they react quantitatively. They will automatically react with anything that's present. What a buffer does, though, is buffer is a solution that resists pH change. You have buffers in your blood. You have buffers in your stomach to keep your stomach acid from eating away at your flesh. In fact, they're the same buffer. They use a bicarbonate carbonic acid buffer in order to ensure that any acid that could damage the body gets negated. And the blood actually uses it as well to make sure that the blood doesn't get too basic, because even a small pH change in the blood will kill you. So buffer solutions have specific pHs and they resist changing those pHs. That's why we have these long, relatively flat regions where the pH isn't changing much, even though we're adding a lot more solution than this equivalence point here. So what that is that's the buffer resisting pH change until the buffer's practically all used up. And then even a little bit of hydronium or hydroxide causes a rapid change in pH. The ability of a buffer to resist longer is known as its buffering capacity. The buffer capacity basically lasts until you get that flat line changing into an exponential curve. And this is basically when enough of the conjugate acid-base pair has reacted that it's consumed one half of the pair. And that's the point where buffering fails and now pH changes start to take place. Biologically, one of the other buffers that we use as well within our cells is a dihydrogen phosphate buffer. And again, because this is a polyprotic compound, it means that this particular ion is also amphiprotic. It can act as an acid or a base. And the really nice thing about an amphiprotic buffer is that it resists both changes towards the acid and towards the base. So that means that it's very, very good at buffering and actually can buffer multiple times as well. And as I mentioned before, the other really important biological buffer is our carbonic acid hydrogen carbonate buffer that we use throughout our body.